So thank you, Miriam, for a very nice introduction. Let us start with the presentation. So if we analyze the current way how the AI systems are implemented, can discover that most of them are implementing within the data centers or in the cloud, meaning that we are using cloud services and cloud devices which are then deployed and are running our AI algorithms. But this situation is starting to change and will certainly change in the upcoming years and in the future. Everybody agrees about that. And the change will come in a form that more and more of AI algorithms will actually move to the edge and will be deployed on the edge and will be executed on the edge. And this is very much true for the AI inference phase, which will certainly move to the edge, while the AI training algorithms will most probably still be executed in the data centers or in the cloud. And why we would like to move our AI processing to the edge? Well, there are several benefits of doing this. First of all, we have by doing so, by basically moving the AI processing close to the sensor or integrating them within the sensor, for example, within the IDS camera, we can reduce the latency in processing this data, because if your AI processing architecture is located within the sensor or close to the sensor, you don't have to move the data far away to some data center or the cloud and waste time while you move the data, then process it on the cloud, and then return the processed information back and act upon it. Instead, you do all this processing locally within your sensor. This also reduces the bandwidth requirements, because there is no need to move any data between the sensor and the processing part, because they are somehow coupled, integrated together. So that eases the requirements when you are developing the system. Moving AI on the edge also improves upon your security and privacy, because again, if the data is processed close to the sensor or within the sensor, within the camera, then no data leaves the system, and hence you have increased your privacy if that is your concern. Also, your security is increased because you don't have this link between your camera and your processing in the data center, which could be attacked by some malicious parties. And also, your processing is somehow distributed over different cameras, and it's not centralized within the data center, which could be then a single point of attack. So your security of your system will also improve if you move your AI processing to the edge. Also, the reliability and availability of the complete system should improve, because it's now tightly integrated within one device, within the camera. And again, there is no this link that can go down or not be available from time to time. So the reliability and especially availability of this configuration where AI is processed in the edge is also improved. And you get also a benefit of customization. If each camera or each sensor has its own AI processing capability, that means that you can basically run a specific AI algorithm on every camera separately. You don't have to have one huge CNN network that should cover all different types of input data that you are gathering in your production plant, for example. You can develop a customized CNNs for each specific camera, each specific sensor that you have deployed. And this can also reduce your development time and your cost compared to the data center solution. So there are obviously clear benefits why we would like to move our AI processing to the edge. But moving the AI to the edge is not so easy. It is a challenging stuff because, as you probably know, edge computing is all about efficiency. On the edge, you have limited amount of compute resources, memory resources that you could use to deploy your application. And you have also strict power requirements, the amount of energy that you can use, either because maybe you are battery operated or you have some thermal constraints. So edge computing is all about efficiency and at the same time requiring significant or high performance values, particularly low latency, which is somehow conflicting these strict requirements about available computing resources. So edge computing is not easy. And this is ever more true if you try to deploy AI on the edge, especially if you are talking about the flagship AI architecture, which are currently CNNs, as you probably know. CNNs are known to be extremely compute hungry, requiring billions of computations to process one input image. They are also memory hungry because they have many parameters, hundreds of millions of parameters describing the CNN architecture itself. So they are clearly not a good candidate to compute on the edge. Therefore, if we are to move them to the edge, we have to optimize them somehow. And there are a couple of ways how we can do it. Typically, what you do, you try to deploy so-called parameter efficient networks when you are doing edge processing, like MobileNet, EfficientNet, SqueezeNet families, which have significantly less number of parameters required to describe them. And this clearly reduces your memory requirements and your compute requirements. But this is usually still not good enough. So the next thing you could do, you could perform what is called a network compression. You can prune the networks by removing some of the parameters, further removing after the training. And you can also perform quantization to reduce the number of bits that are used to represent each of these parameters. So pruning and quantization further reduce the memory requirements, the size of memory you require to store your CNN. And also, if the processing, CNN processing part is designed in a specific way, you can also benefit in terms of processing time when you're operating on pruned networks. And this leads me to the final piece of the puzzle when we try to deploy AI on the edge. And that is the requirement that even with this usage of parameter efficient networks, further compressing them, we still have to use a customized computing system, specifically tailored architectures that are efficient when processing, for example, CNNs. So what can we choose from as a base for our implementation of the CNNs on the edge? Well, basically, we are concerned with two things. One is the flexibility, meaning that our system should be as flexible as possible, in a sense that if the CNN architecture changes due to some new developments in the research area of the CNNs, and bear in mind CNNs are extremely are still being developed. Let me put it that way. We are seeing new developments, new layer types, new architectures appearing on a monthly basis. So it would be great if our system for running CNNs on the edge should be capable of supporting all these new developments. At the end of the time, it should be efficient, as I said, because we are doing edge computing and we should be efficient. So what options do we have? We could choose a CPU-based system. That's an obvious candidate. This would give us great flexibility, as you all know. But at the same time, CPUs are extremely inefficient in running CNNs, especially they are not power efficient. So CPUs are obviously not a good candidate. They have great flexibility, but very low efficiency. The next thing that you could choose is a GPU platform. The GPUs, although being more specialized than the CPUs, are still having a great flexibility in supporting different CNN architectures. And they have much more performance, as you all know. But their power efficiency could be a concern when we are deploying them on the edge. The next candidate would be an FPGA platform. As you probably know, the FPGAs are programmable devices, meaning that you can change the architecture of the FPGA device on site in the field, which is a great stuff, because that could give us great flexibility. We could change the configuration of the FPGA device as the CNN architecture changes. But this is not easy, because it requires, if you do it in a traditional way, it requires a very specific hardware knowledge to do it. Therefore, the flexibility of the FPGA platforms, if they are used in a traditional way, is not so great. On the other hand, because we can customize the underlying architecture, we should get a great efficiency when using FPGAs. And of course, we can opt for a full ASIC solution, which is an obvious winner in terms of efficiency because it's a custom-made integrated circuit specifically optimized to be efficient in running a specific type of CNN architecture, but its flexibility could be a concern. If some new major developments appear in the CNN field, it is highly likely that our current ASIC platform will not be able to benefit from it simply because it's not designed to process these kind of new CNNs. Nobody knew that they will appear 2 years ago when this ASIC was developed. So the flexibility could be a great concern when deploying an ASIC solution. So which technology to use? Well, that's still an open question. But we in the IDS strongly believe that at this point in time, the FPGA technology is a clear winner. Because of a number of reasons. First of all, as I said, FPGA technology allows you to be customizable. You can always reprogram the FPGA, download a new configuration file, change its underlying hardware architecture, and that gives you possibility to optimize for specific types of CNNs, to build a custom configuration for different CNN types, which will obviously reduce the power requirements and enable you to have higher performance if you do things correctly, of course. Furthermore, FPGAs are known to have a longer lifespan compared to GPUs. So their lifespan is usually 2 to 5 times longer than GPUs. GPUs are mainly developed for gaming. They can be used in machine learning field. They are intended to be used in a home environment with the control environment conditions and all that. And basically, if they are deployed in an industrial environment, their reliability will start to show. And FPGAs, on the other hand, are highly reliable devices with much longer lifespans, which is also important if you are thinking about industrial applications. And I think the major factor why FPGA technology is a good candidate for deploying deep learning or CNN is its reconfigurability. As I said, you can easily reconfigure the structure of your FPGA device in the field, meaning that you can have a deployed camera and you get an update with a new configuration, a new version of the accelerator, which can then easily support any new developments in the CNN algorithms that happen over the time. If you're able to update your FPGA configuration, you're able to support new types of, for example, CNN networks that will appear in 2 or 5 years. And this makes FPGAs a clearly better solution than, for example, ASIC solutions. But we still have to solve one problem, and that is this thing that is known as an issue which is called difficult to program, that FPGAs are difficult to program by a regular user, which is certainly the case. But we can work around this, and this is what we did in the IDS. So our approach was the following. Instead of basically developing a number of FPGA configurations for different types of CNNs, we have opted to implement one universal overlaying architecture. So basically we configure FPGA only once, and it becomes a universal CNN accelerator. Universal in a sense that it can run any CNN network, provided that it is composed out of supported layers. And what layers do we currently support? Well, all the regular layers like convolutional layer, depth-wise convolutional layer, different types of pooling layers, fully connected layers, adding layers, squeeze and excite layers, and so on. So basically, any major layer type is already supported by our DeepOcean accelerator. And this basically completely removes this difficult to program issue, because the user, the customer, does not have to have a specific knowledge in order to generate a new FPGA configuration if it wants to change the network, CNN network that it should run on the camera. This is completely not necessary. You have one universal accelerator which sits in the FPGA and operates on a binary description of your CNN network, and I will come to this later. So basically, if you provide this binary description of the CNN network, that's a description of layers from which the network is composed of, the Deep Ocean accelerator will accelerate it. So if you want to change the network you would like to accelerate, the only thing you need to change is this binary description. So it's really easy to program this accelerator, let me put it that way. And this gives us great flexibility because you can run different types of CNNs, and we are constantly updating the Deep Ocean accelerator in order to support any new major developments in the CNN field. So periodically, you will get an update to your IDS Next camera. And with this update, you will get improved functionality of the Deep Ocean accelerator. And suddenly you will be able to execute new types of CNN networks that appeared recently in the field. So this gives us a great flexibility, as I said, and great support of the newest deep learning algorithms. And we do this for you. So you as a customer don't have to know about these details about new CNN layer types or CNN architectures. We provide a new version of a Deep Ocean accelerator. You upload and update your camera with it, and suddenly you're able to run your newest CNN networks. And because we have a tool that, and I will shortly talk about it briefly, a tool that basically generates these binary descriptions out of your existing, for example, the TensorFlow or Keras CNN models, we have a reasonably good support of different deep learning software environments that you are familiar with and would like to continue to use it and still be able to benefit from our IDS Next camera. So how does the CNN implementation flow using a Deep Ocean accelerator looks like? Well, it's composed out of three relatively simple steps. The step one is obviously to define your network and to train it, for example, using the Keras environment. And then we recommend also to prune the network. By pruning, you are removing some of the connections, some of the parameters from the network. And we provide a tool that you can use it to actually prune the CNN network. By pruning it, you are removing the parameters. Therefore, you are reducing the memory size required to store the network on the camera. And by pruning it, you can also be more efficient when processing input images by pruned networks, because you can skip some of the computations, because some of the connections between the layers are non-existent anymore. So there are clear benefits when pruning the networks in terms of processing performance and their size. But what is maybe important to you is that this step is optional. So if you don't want to prune your network because maybe you don't know how to do it, you are concerned with the end results or whatever reason, you don't have to do it. So this pruning step could be skipped. And then it means that you are doing the regular stuff. You are defining your network, you are training it. And when you are happy with the performance of your trained network, you either prune it or not and proceed to the step two. And this step two actually performs this translation. So you have your Keras model in a Keras language, in a high level description, which obviously cannot immediately run on the Deep Ocean accelerator. It has to be translated in some sort of binary format. And this binary format we call a linked list representation. So each layer from your network, from your CNN, gets one node descriptor in this linked list. And this node descriptor actually describes this particular layer of your CNN. And then by stacking layers, you are adding nodes, and you're at the end finishing with a complete linked list binary representation. So this representation is in a binary format. And we also provide a tool that does this automatically. So you simply invoke the tool, and this translation process is done automatically. You input to the tool your Keras model, and at the end result is this binary file, which can then be downloaded to the camera in step 3. So this binary file will be now downloaded to the operating memory of the camera, and DeepOcean Core will start processing it. And that's it. You are running your CNN network on the IDS Next camera with the DeepOcean Core. There are clear benefits in using this linked list binary description. And I will only talk about the most important one. Having this approach, having a universal accelerator and having this linked list binary representations, it is easy to switch between different networks at runtime. So you can have in the operating memory of the IDS Next camera, you can have a number of different binary descriptions of different CNN networks. CNN description 1, 2, N. And all of them are already in the memory, ready to be processed by the DeepOcean Core. And how do you select which one to process at any given time? Well, basically, you have to point the DeepOcean accelerator to the beginning of the binary linked list representation of the CNN network that you would like to run. And if you like to change the networks, the only thing that needs to be changed is this pointer value, where the linked list starts in the memory. So this change is easy. It's basically one register write, and therefore it's extremely fast and gives you the opportunity to change the networks on the fly. What you could also do, you could even change the topology of the network if you like. So for example, you have one network with one stack up of the layers, and now you decide that you would like to remove this layer and replace it with this one. So, and you do this dynamically under the operating conditions, for example. This is also easy because this is a linked list. You rearrange a couple of pointers and you have effectively removed this layer and introduced this one. And all this works seamlessly and it's extremely fast. And why this dynamic switching of networks could be interesting for you? Well, I have one example. For example, let us assume that you have a production line and you have two types of products going over this production line. In this image, this would be these apples and pears, and you would like to inspect them in terms, meaning that you would like to detect the position of each of these objects on the production line. And then based on its underlying class, is it apple or pear, you would like to inspect them for some class-specific faults. For example, apples have faults 1, 2, 3 to N, for example, and pears have different types of faults. And basically, you have to do, you would like to do some anomaly detection, for example. And how this can be achieved if you don't have this dynamic network switching? Well, you could train one big complex CNN network that first has to, or at the same time, has to do object localization. It has to localize these objects and then also perform the classification. So first localize and immediately also classify. And this is certainly possible, but it will be extremely difficult to train. This network will have to be huge. It will be difficult to train. It will be most probably difficult to achieve high enough accuracy by approaching this problem like this. But you could approach it differently if you have the capability to switch CNN networks on the fly. So you could now decouple the localization and train your only object localization network. And this network should only localize two classes in any image. So it looks for apples and pears. and that's it. It does not further classify the apples or pears into subclasses to look for some faults or defects or anomalies. It's simply concerned with the localization. And this is much easier task compared to this huge complex network. So it is reasonably to expect that the required network will be much smaller, hence much faster, and much easier to train, because this is a two-class localization problem that's, okay, it's certainly not trivial, but it's not as difficult as this one. But this is not a complete solution. Now we have only localized our objects, but we now want to do anomaly detection, which is somehow specific to each class. So we are not looking for the same anomalies in apples and in pears. So obviously what we can do, we can now train additional CNN networks, which are now doing classification only. And we can train one CNN network, which is specialized in anomaly detection in apples, and another one, which is specialized in anomaly detection in pears. And we can determine which one to run on the fly based on the current situation. So if we are now processing apple, we will opt for the apple classification network. If we are processing pear, we will opt for a pear classification network. And this can be done very easily within the IDS Next camera. So you have this capability to basically select which network to run. And this would be this red network. So this gray network does the localization. If we want to classify further the apples, then we run the red network. If we want to further process the pears, we run this green network. And all these networks are now specialized. They have to solve much easier task than this huge complex one. So they will be easier to train, and they should be smaller in their number of parameters and therefore faster in execution. So this setup could at the end be much more efficient, even in the terms of processing, than this original setup. And it should be much easier to develop. And it should have much higher accuracy in doing its work compared to this solution. But this approach clearly requires dynamic changing of the networks on the fly. But IDS camera allows you to do something like this quite easily. And finally, to conclude this presentation, I talked at the beginning that edge computing is all about efficiency. So I would like to conclude the presentation with some performance numbers of the DeepOcean, the current version of the DeepOcean. Bear in mind that we are, as I said, we are constantly improving the performance and capabilities of the DeepOcean accelerator. So expect these numbers to improve over time. So you can see different types of CNN networks. So all these all these rows, except the last two, actually show the performance of image classification networks. And you should particularly pay attention to the performance numbers of these parameter efficient networks: MobileNet family, SqueezeNet family, and maybe EfficientNet. The table also presents the results for the Inception and ResNet families, but they are considered too complex for the edge-based applications. But you see, still the performance numbers are reasonably good even for these types of CNN architectures, and for the parameter efficient architectures, the performance numbers are over 20 frames per second, which should be sufficient when deploying them on the edge. Something similar can be said for the object localization networks, and these are these last two rows. You still get around 20 frames per second when running these networks on the DeepOcean core. And as I said, these numbers will only improve over time because we are constantly improving the performance of the DeepOcean core. What is maybe even more important when you talk about edge computing is the power efficiency. And a good metric for that, for comparing different solutions, is so-called inference efficiency, meaning how many images per second you can process by your system per 1 watt energy. And on this graph, you can see this inference efficiency of different types of CNN accelerators, the deep ocean, the GPU solution, Jetson TX2, a classical CPU solution, an embedded CPU solution, and a fully ASIC solution. And if you see this graph, especially for parameter efficient networks like MobileNet V1, V2, and SqueezeNet, you can see that the deep ocean architecture is a clear winner, at least when compared to these competing solutions. It has the greatest inference efficiency among them all, which makes it this is a further statement that the deep ocean is really a good candidate for selecting it for your edge-based AI system. And with this, I would like to conclude my presentation. Thank you very much for your time. I hope you enjoyed it. If you have some questions, of course, I'm open to it.